Since we'll be utilizing sinusoids extensively in this module, here's a very quick review of what sinusoids are and some of the most useful trigonometric identities that we'll be using. So first off, I'll start off by sinusoids can be represented as sine or maybe cosines. Either way, it's fine. Both of them are called sinusoids. I'll use sine to explain in here, even though that typically in phasor transform we use cosine. But anyway, so what we have is we have a sinusoid, and I defined it in terms of x, but frankly speaking, x could be current or voltage, depending on which one we're looking at in terms of circuits. Okay, so the current will be a function of time, the voltage will be a function of time. And what we have in here is we have first here, we called x of m, and that's basically the amplitude or magnitude, sometimes it's called. So it's amplitude or magnitude. Okay. And of course we have sinusoid, and the omega is what we call an angular frequency. Okay. Frequency. So an angular frequency has the unit radians per second. By the way, the units for the x in here and the unit for x in here depends on whether it is I or V. So if it's I, it's milliamp, amps, or so forth. And if it's volt, kilovolt if it's a voltage. And then, of course, we have t. This is basically our independent variable. And here what we have is we have phi. Sometimes we refer to it as theta, or we use theta, not refer to it as theta. And I'll be using phase in here because we talk about phase angle. Okay, or that's why we use phi or phi, and its unit is radians. All right, so this is how we define it. Well, the way this looks is actually similar to what we see in here. So what we have is a sinusoid basically goes back and forth, up and down, and sinusoids, as you probably know, are what we call periodic. So if you take a point in here, it comes back to the same point, and it takes it exactly t, uppercase T. So the t is what we call period, okay? And the period is measured in seconds. So if you take the reciprocal of the period, which is 1 divided by t, that will be f. Okay, and that f is just simply what we call linear frequency, or short for frequency. And typically its unit is in hertz. Okay, nobody says like pulses or per unit of time. We just utilize hertz. And if you take omega, which is the angular frequency, is just simply 2 pi times f, okay? And its unit, again, is radians per second, or sometimes is written 2 pi divided by t using the period. Anyway, the unit is radian per second. Okay, how about the x of m? What's the point of x of m? Well, as it turns out, sinusoids, sines, cosines, whatever it is restricted to the values of -1 to 1. So this magnitude or amplitude will change that restriction. So now whatever you see in here is affected by x of m. So you'll see that it's approximately -4.5 to 4.5. This is because x of m is that way. And sometimes what we have is we have different sinusoids at the same time, and we need to compare them. This is something very typical if we compare like the current at 2 different elements, for example, or the voltage at 2 different elements. So what we end up with is equation look like this. X of 1 of t is basically x of m sinusoid, and then omega t, and then another x of 2. It will have a different magnitude, but for now, for the sake of simplicity, just so that I explain it, I'll assume that they have the same magnitude, the same frequency as well, but different phase in here. So in here, I'm showing you an example of that. So let me just color them with the same color. So this one here is x of 2. Okay, I'm going to color it. So let's think about it. One is actually happening before the other. So this one here has a phase of 0. So it's exactly at 0. Whenever the sign is 0, it will be exactly 0. So if you think about it, this is basically the black one in here. So this one here is the black one in here. So let's do that. I'll just highlight this, and I'll just select the color to be black so that we can reflect it. All right. That means the second one in here is actually the one in red. Okay, so this one here is in red. So that's what we see in here. And we can think about it in here. So this one here is x of 2, and this one here is just simply x1 of t, of course. Both of them are functions of t. And we typically say, well, let's think about it in here. What you see, let's take a look at the maximum value. So the red one reaches the maximum value before the black one. So it actually leads it. And you can think about it in here. You'll see it, that it actually has a phi. This one does not have a phi. And in this particular example in here, I'm showing you the phi of actually exactly 50 degrees. That's when I actually plotted them. So there's a 50 degrees difference between them. Okay, and as it turns out to be, we say that x of t leads x of 1 by 50 degrees. Or sometimes we say x of 1 actually lags behind x of 2 by 50 degrees. Leading meaning x of 2, the value in x of 2 happens first and then in x of 2. And you can see it throughout. You will see that it's actually just a little bit, it happens before in the red before it happens in the black signal in here. Okay, so now we know what a cosine and sine is. Just very quick trigonometric identities that are helpful. There's many others, but these are the ones that we'll be utilizing. So we'll see these ones here, for example, if you have the sine of a plus b, what you do is sine a times cosine b plus cosine times sine. And you can see them and you can read them slowly. Whenever it's a sine, the sine, if this is positive, this is positive, if this is negative, this is negative. The cosine is slightly different. So you'll see the cosine here has a cosine versus a sine cosine before, and then a positive in here, a negative in here, and this one here, negative in here, positive in here. So examples of the usefulness of these trigonometric identities are here, and I've written them for you. You can pause the videos and just read them, but the idea is if you have a sine and you want the negative of that sine, all you have to do is just add or subtract 180 degrees. This is very similar to the cosine. More interestingly is actually if you want to convert between sine and a cosine, because as you remember, a sine and a cosine, like if I have something like this, I can figure out what the sine is here and the cosine is here, but the point is exactly at the same place in the circle. So we can convert a sine to a cosine or a cosine into sine, but just adding or subtracting 90 degrees, whether we want the negative or the positive. So let me show you an example of this. So an example of this is here. So what we have is we have some sort of a signal and it's represented in cosine. And let's assume for some reason or another, you want to represent it in terms of sine. It's still sinusoidal, it has the same frequencies and everything. So what we do is we can use one of these identities in here to write it. Specifically, we'll be using this because what I have originally is the cosine, so I need to add or subtract 90 degrees in order for me to get the sine. Okay, so let me just do that here. So what do we do? Well, I'm going to do 20 cosine, and I'm going to do 6 of t, then plus 45 degrees, okay? And what we can do is the following. We can either add and subtract 90 degrees depending on what we're trying to do. Well, what we're trying to do is we're trying to get the positive. So what I'll do is subtract negative 90 degrees. But this will give me a completely different sinusoidal. So what I also need to do is I need to add the 90 degrees in here. So that's what happens. So let me just explain. What I've done is I subtracted 90 degrees and I added 90 degrees. So effectively, I didn't change anything from here. So both of these are the same. But now we know that a cosine of omega t negative 90 degrees, for example, will give me a positive sign. So I can rewrite this as 20. And now here are the changes. Sine, okay, this is one of the changes. Okay, 6 of t plus 45 degree. And I've already utilized the negative 90 degrees. So I have utilized it to do that sign in here. So what I need to do is I'd say plus 90 degrees. Of course, I can add the 45 and the 90 degrees, and what I get is 20 sine 6 of t plus, I believe that will be 135 degrees. So all of these are equivalent, so I can just say equal, equal, equal. So effectively, I can rewrite this as 20 sine 6 of t plus 135 degrees. Okay, and just a quick comment about the degrees and whatnot. So if you take a look at when we covered the sinusoids and everything, well, we said that omega t is radian per second, and this is second. So this is, let's assume this is radian per, here. This is radian per second, and this would be second. So the whole thing will be radian. So technically, the phi should be radians. However, convention says, like a lot of the times what we do is we imply that this should be radians in here, but what we do, because it's simpler, we use degrees. And hopefully you remember that the degrees is 180 degrees is simply pi. So if you need to convert any whatever signal, for example here, the 135, if you wanted to convert it to radians, all you have to do is just basically multiply 135 times pi divided by 180 degrees. So if you want the equivalent to this in radians, multiply by pi divided by 180, you get that value if you want to compute that for some reason or another. Anyway, so that's how we convert a sine and a cosine. However, it is a little bit tedious to just remember these equations in here. So what I usually do, which is not very mathematical, but it helps, is I actually draw this diagram in here graphically, okay? And I'll say, well, this one here will be positive cosine, this one will be negative cosine, this will be positive sine, and this one here will be negative sine. Okay. All right, so what do? Well, I'm going to assume that, well, I know the difference between here and here is just simply 90 degrees. But what I can tell you is if you move counterclockwise, you will have to say add 90 degrees. And if you move clockwise. So the positive 90 degrees was counterclockwise. This is clockwise. This will be 90 degree. So how is this useful? Well, I don't have to do this in here. Look, so I'll be translating this using that diagram. So let me show you how we can do that. So the way I'm going to do it, I'm going to rewrite 20 cosine 6 of t plus 45 degrees. Okay. So what I can tell you is, well, I'm at the cosine. What I need to do to move to the sine is actually add a 90 degrees. Okay. So all I have to do is just tell you 20. I'm going to move it to sine 6 of t plus 45 degrees. And now I'm going to add the 90 degrees. And this is exactly what we ended up here. So I didn't have to add, subtract, and just figure out which of the equation should I be using, especially if there's a positive in here, negative in here. All I have to do is just basically do that. So now let's assume I want to convert this one. Well, the result in here, of course, is 20 sine 6 of t plus 135 degrees. We know that because we got that solution like a little bit before, like a few seconds ago. So now let's assume that I have this, and what I want to do is to convert it to a cosine, for example. Okay, so what you can do is I'll take a look. Well, the sine is in the positive in here, and the same thing here for the cosine. That's why I moved from here. So what I need to do is I need to move from here to get the positive cosine. So this tells me you have to move clockwise 90 degrees. So I have to subtract 90. So this tells me it's the same as 20 cosine 6 of t plus 45. Well, not 45 because we're at 135 degrees. We're converting this one now. Okay, and what I need to do, because I'm converting it from sine to cosine, is actually subtract 90 degrees. And that will be 20 cosine 6 of t. 135 minus 90 degree, hopefully we'll get, we should get 45 degrees because this is where we started with. All right. Maybe another example just to clarify things a little bit. So the second example that I'm giving you is the following. So I'll assume that two signals in here. I have x1 of t, and that happened to be -5 cosine omega t, and I'm not telling you what the frequency is, okay? And it doesn't matter when we convert from cosine to sine or so forth. And I have another x of 2 of t, and that happened to be 12, and this is sine, and this is omega t, -15 degrees. So a lot of the times what you'll be asked, or what you'll be wondering, is like, well, which one leads and which one lags behind? So there's a few things in here. Well, the first is one is in cosine, the other one is in sine, so I can't compare them. And frankly speaking, this is a negative sign, so we can't really compare them. And the other thing is this one has a phase difference and this one has a phase difference. Okay, so we can't technically figure out which one is leading, which one is lagging. Of course, if they share the same frequency, they're moving both at the same rate. So if one is leading, it's leading all the time. And if one is lagging, it's lagging all the time. You might tell me, oh, it's simple to do. All you have to do is just basically plot them in here. So this is a cosine and sine, and figure out, well, this is cosine and 35 degrees. So we move in here by 35 degrees, for example. Okay, well, why don't I just do it? You can do it that way. I can do it graphically, but I think I don't need to do that. And the other one is a sine of -15 degrees. Probably here is here, -15 degrees, because this is where the sine is, this is where the cosine is. So one is in here, one in here. This is x1, this is x2. So I think x2 will be leading x1, because if they're both rotating that way, x2 will always come first, so x2 is leading. But anyway, this is one way to do that. Better way to do this, more mathematical, is let's convert both of them to the same, either both sines or both cosines. And I'll do it in both methods in here. So I'm going to do this one here. I'm going to say method 1. And in method 1, what I'll do is I'll bring this diagram in here just so that it helps me convert sines to cosines and so forth. So we'll do that, okay, and I'll copy it. And I'll tell you here, this is based in here. Let's double check. So what I'll do is I'll convert both of them to cosine. Okay, so that tells me x1 of t. I need to convert that to positive cosine. So of course, if I'm at the negative cosine, I need to move to the positive cosine. I either add 180 degrees or subtract 180 degrees. Both of them are the same. Okay, so I will be adding 100 degrees. So that tells me 180 degrees. 5 cosine omega t plus 35 degrees plus 180 degrees. Okay, and I already got rid of that negative in here. Okay, we compute what that is. That's 5 cosine omega t plus, that is 215 degrees, and that's basically x1 of t. All right, so let's see what x2 of t is. x2 of t, well, in this case it is in sine, and I'm converting everything to cosine. Okay, where is the sine? The sine is here. I want to move to cosine, so that tells me subtract 90 degrees. So we'll end up with the following. Okay, let me just write it in red, I think. Okay, and that is 12 cosine omega t minus 15 degrees minus 90 degrees. And that is basically 12 cosine omega t, I believe negative 105 probably, yes, degrees, and that's x2 of t. Alright, so now we have x1 of t and x2 of t, both of them are cosines, so we can actually figure out which one is leading, which one is lagging. You can plot them as well, and you'll see here. So let me just plot those. So what we have is we have the following, we have this one in here, okay? And what we have is, this is the cosine, okay? This is, we wrote everything in terms of cosine, so that's what we care about. So what we have is the first one here, and I'm gonna do that in blue. So we have from here to here, that will be 90 degrees. This one will be 80 degrees. We're above 80 degrees. We're at 215. This will be 270 degrees in here. So the 215 is somewhere around here. It is specifically like 35 degrees below the 180. So it's here, like basically 35 degrees in here. I don't care about that. It's 35 degrees. What I care about is it's between here and here. It's actually 215 degrees in the positive, okay? And that here is x of 1, okay? What about x2? Well, x2 is actually also based on the cosine. What we need to do is we need to move negative 150, so we're going to move that way. So if we stop in here, that will be negative 90. This is negative 180, so it's basically somewhere in this quadrant. And specifically, it will be somewhere around here. This will be about 15 degrees. I mean, they're not up to scale, but you get the idea. This is 15 because you know, if we said that this is 35, this is not 15. It will be half of that. But anyway, so you get the idea here. What matters is from here to here, it's actually negative 105 degrees, okay? And that basically x of 2. And we did say that x2 is leading based on this diagram that we have in here, and that's exactly what we saw. If both of them are rotating this way, you'll see x2 is always in front of x1. So what's the phase difference between them in here? Okay, you can of course use the diagram to figure it out, but actually we have these numbers. It's actually between the 205 and so forth, so we can compute them, and that will becomes basically well, we have one in the negative, one in the positive, so I need to convert the positive. For example, this one here, I can convert it to 12 cosine omega t, and I'll just have to add 360 degrees. So 105 minus 360, that becomes positive 255 degrees. So from here to here, that tells me is 255 degrees. That's what it tells me. Okay. And okay, so what's the difference between them? Well, the phase difference is basically 255 degrees because it's leading minus the one that was lagging, which is 215. Okay, so 255 minus 215 is just simply 40 degrees difference. Okay, so x2 is leading x1 by 40 degrees difference. So we got it that way. We can also get it using converting those into sinusoids. So instead of sines and cosines, we can convert them to sines. So let me just do that. We did it by converting to cosines, and that's okay, and you can stop there, but we can do the same thing using sines. So let's do that using sines. So what I'll do again, I'll take this one here to help me convert, okay? And usually I have it memorized, but you don't have to at this point, okay? All right, so what I'll do is I'll convert this x1 into its equivalent in sines. So x1 of t, or where am I? I am here. I need to move from negative cosine to the sine. So what it tells me is go clockwise by 90 degrees. So do subtraction by negative degrees. So what you get is 5 of sine of omega t. And then what we have is positive 35 degrees. And then we're going to do negative 90 degrees. And that tells me it's 5 of sine of omega t of negative 55 degrees. Of course, we can convert this to positive things as easier. 360 minus 55 is basically 305 if you wanted to. Either way, 5 of sine of omega t, negative 50 plus 360, it becomes plus 305 degrees. Okay, so that's x1 of t. So let's do x2 of t. So x2 of t is already in a sinusoid, so I don't have to worry about it that much. Okay, but what I will do is instead of having it in the negative in here, I'll add 360 to that 15. So 360 minus 15, that becomes plus 345 degrees. Okay, so that's x2 of t. So let's plot these just to see them. Okay, and what we have is the following. Now, our reference is the sine, by the way, as opposed to the cosine that we've done previously. So we can either take the negative in here and negative in here and just deal with it that way, or 305 and 335. I'll just deal with the negative for now. So x of 1 is actually negative 55 degrees. Negative 55 degrees, I think it's half, like 45 degrees is halfway, so from here to here. So from here to here, because it's based on the sine, this is negative 55 degrees. I'm also telling you that if you go from here to here, what you will end up with is 305 degrees. That's basically what you have in these two in here. All right, let's do this. Let me just make sure I highlight that this is basically x1. Okay, what about x2? Well, x2 is in here. It's actually from here to here. It's actually from here to here is negative 15 degrees. Okay, or I can say from here to here, okay, that's 345 degrees in here. And that basically here is x2. And again, if both of them are rotating this way, we can see that x2 is leading x1. By how much is it leading? Well, simply 345 minus 305, and that's basically 40 degrees. And that's exactly what we found using the cosine here. So how to, so x2 is leading x1 by 40 degrees.